Purvang, you can start now.
Okay, thank you. So please let me know if my screen is visible. Is it visible?
Yes, sir.
Okay, good. Thank you. So, hi guys, my name is Purvang Mantri, and I am an author, an educator, and a content creator. And to just give a small introduction about myself, then I have done my diploma and bachelor's in automobile engineering from Parul University, Vadodara, and postgraduate diploma in electric mobility from College of Engineering, Pune, with collaboration with ARI Academy. Okay, so in today's webinar, we are going to talk about electric motors, and we will look into different types of electric motors that are available in the market and that we prefer to use in our electric vehicles. And simultaneously, we will look into how to size a motor. That means how to select a motor for whatever kind of vehicle that you are designing and or developing. Okay, so to start, let's first browse with the basics of electromagnetism or law of induction. We are aware about Faraday's law of induction, and we have learned all of this stuff during our school times itself. But still, I want to brush all of these topics before we head into the working of electric motor. So Faraday's law of induction states that whenever a conductor is placed in a varying magnetic field, please mark this word varying magnetic field. It actually induces an electromotive force inside that conductor or within that conductor, and it produces an electric current. So this Faraday's law of induction is playing an important role in various electrical machines like transformers and motors and generators. And this is the back end, or this is the base for every electric motor to function. Okay, so based on this law, a basic electric motor functions, and we have learned this working principle of electric motor in our school times. We know that when we place a coil between a magnetic field, and if you pass current through it, then according to the Fleming's left-hand rule, the thrust will be generated in the upward direction, and it will make the coil to rotate. But once this coil has reached to its uppermost point, there is a tendency that it can go back to its original position. It can go in reverse position. So to rotate it through an entire revolution or go through 360-degree rotation, we need to change the polarity of the electric current passing through this coil. And for that, we need to use something called as commutator and brushes. So this is the reason why, basically, this is used in DC motors, where we are using direct current as the power supply for our electric motors. Then we need to provide something called as commutator and this brushes. But this is the basic principle of DC motor, and there are various types of motors which are used in our market. We are aware there are DC motors, simultaneously we have AC motors, and in both DC and AC motors there are various types. First and foremost, we have the brushless type. Everyone is aware about BLDC motor, and we are going to look further deep into it. And simultaneously, we might have learned about brushed DC motor. And the example that we looked into in this slide, this is actually a type of brushed DC motor. This is like the basic working principle of a brushed DC motor. Okay, the one with permanent magnet. And there are other types of brushed DC motor in which instead of using permanent magnet, they uses windings for the stator and rotor. Okay, in this case, in the basic DC motor case, in the basic example of brushed DC motor which uses permanent magnets, yeah. Okay, if that is a question, then you can ask right now, or else if you're just checking your mic, then no worries. We can discuss the questions in the later part. Okay, so in this case, we are using magnets in the stator, but there are DC motors in which we use magnets in the rotor as well. Those are the brushless type. Okay, so we are going to look into that, but we are not going to look into the motors which uses windings on both stator and rotor, which are these series shunt and compound wound motors, because they are not used in electric vehicles, and that's why we have kept it aside for this session. On the second side, we have AC motors. AC motors are basically two types: synchronous AC motors and induction motors, and that too based on the power supply single phase and three phase induction motors. Okay, so let's first look into the brushed DC motor. And this is like the basic, as we started this session, we looked into the basic working principle of an electric motor. That was the best example of a brushed DC motor. So we, in this working principle, we saw that there was just one winding, there was just one coil, which was placed within a magnetic field. But if we want higher torque, then we need to increase the number of windings in the rotor itself. So that's why in brushed DC motor, we have number of windings provided or wound in the rotor part of the motor, while magnets are connected or magnets are mounted on the stator part of the motor. Okay, and as we saw it earlier, we use brushes and a commutator to provide electrical current to the windings of the stator, or I'm sorry, rotor. Okay, now the issue with as the current flows through this, it flows from the brushes to the commutator and through the windings, and it sort of creates an electromagnet. Like the rotor becomes an entire electromagnet, and the electromagnet attracts and repels against the magnetic fields of the stator, and that's how the rotor part of the motor rotates. Now, one of the issue with this type of motor is that as soon as the rotor rotates, as soon as this gap of the commutator comes in contact with the brushes, zero current is flowing through the windings. I mean, in this case, we have only two commutators, but in actual cases, there are multiple commutators used in the DC motor. So in this case, we are seeing that only two commutators are used, and it is split at this particular point. So whenever this point comes in contact with the brushes, no current would be flowing through the windings. And at this point, there will be no torque generated. So this is the reason why, and this is one of the reasons why it creates a torque ripple. Like as soon as, because of the momentum, the second commutator or the next commutator will get connected with the brush, and it will again start rotating. But because of this because of this disconnection of electricity, it actually creates a torque ripple. Simultaneously, there is some arcing going on between commutators and the brushes, and it tends to wear the brushes out. So this type of motors require some maintenance as we use it. And that's why we don't prefer brushed DC motor in our electric vehicles. We prefer something called as brushless DC motor. In this case, we have just inverted the components. Now, in brushed DC motor, we were using magnets on the stator and windings on the rotor. But in brushless DC motor, we have windings on the stator while magnets are connected on the rotor. And to make the magnet rotate, we are generating a rotating magnetic field. So you can see, like in this graphical image, in this animation, you can see that the magnetic fields are changing from stator windings to windings. Okay, and this is done in such a way that one stator winding would be attracting the magnet pole, like the rotor magnet of the rotor, while the other stator winding would try to repel it. So because of this repelling and attraction, the permanent magnets of the rotor would keep rotating, and it will generate high amount of torque. And there will be pretty minimal torque ripple compared to brushed DC motor. And to switch on the windings of these stators, we use something called as, like electrical and electronics engineer would know this term as ESC, electronic speed controller. But in our case, being an automobile engineer, we call it MCU, motor control unit, or motor controller in short. So motor controller is nothing but an inverter and rectifier together. Inverter is used for inverting the DC current into a sort of an AC current. It's not a proper AC current, but a sort of AC current, because it will, what will MCU do or motor controller do? For each winding, it would switch on the winding for a certain period of time, it will turn it off, and then it will reverse the polarity for the winding so that the polarity of the magnetic field changes. Okay, and that's how it creates a sort of an AC current, not a proper AC current. AC current is sort of like AC current is sinusoidal, but when it comes to DC current is straight. Like it is a direct current, the voltage does not change with respect to time. But for brushless DC motor, we need to switch the current so that the windings can switch the polarities, and that's why we need to switch the we use a motor control unit to switch that current sides. Okay. Now these were the two basic types of DC motor. Brushless DC motors have been used in pretty like many vehicles by now, and they are highly desirable. something similar we have we have something similar in AC motors as well, which we would call them PMSM motors. We are going to get to know them pretty deeply in this session as well. Okay, now let's move to the different types of motor which are like based on the current supply that we provide. They are the AC motors, and first and foremost we have the induction motor. So as the name says, induction. In induction motor, there are basically two types. One is the squirrel cage motor and other is the slip ring motor. So first and foremost, we are going to look into the squirrel cage motor. So squirrel cage motor does not have, like, we don't need to provide any electrical input to the rotor part of this motor in squirrel cage. This is the rotor of squirrel cage motor. And you can see the rotor is made of iron bars, which are mounted at a certain angle. The reason for this angle is to provide better torque. And what this motor does is, it's all in the name, induction. The stator windings induces magnetic field, like they create a rotating magnetic field, and that magnetic field will induce a current in this rotor, and that that induced current in this rotor will have its own magnetic field. And that magnetic field, the magnetic field of the rotor, which is induced, will attract and repel against the magnetic field of the stator. And that's why it is known as an induction motor. That's how it will rotate. It will make the rotor to rotate. Okay. So there are different types of squirrel cages as well. Like in this case, only bars have been used, but there are other types of rotors in squirrel cage where this laminated iron sheets have been placed within the rotors as well. Okay. But one of the issue with induction motor is that as the stator is inducing current and then using the resultant magnetic field of the rotor to rotate the squirrel cage rotor, the issue with this becomes that the initial torque is very less. It becomes pretty hard or pretty difficult to get the induction motor to start. And to overcome this, slip ring induction motor came into existence. So this is the rotor for squirrel cage induction motor. And as you can see, yes, there are windings on the on the slip ring, on the rotor part of the slip ring induction motor, and these are the slip rings you can see over here. So this is a type of three-phase slip ring induction motor. Someone's microphone is on, so it is sort of creating a disturbance. Yeah. Can you please turn it off? Yeah. So these are the slip rings that provide the current to the windings of this rotor. Okay, in slip ring induction motor, we provide an input, an electrical input to the rotor as well. And because of providing an electrical input, like we are generating a magnetic field in this as well. And both the magnetic field of the stator and the rotor now can attract and repel each other, and that's how this rotor can rotate and provide better initial torque. Okay, now there was, like, I would like to give you guys a difference in this. Like in DC motor, in brushed DC motor, we were using something called as commutator. While in induction motor, in slip ring induction motor, we are using something called as slip rings. Okay, now the reason being that in DC motors, we are using direct current, while in AC motor, we are using, this induction motor, we are using alternating current. So in DC motor, we need to switch the polarity in the windings so that it continues to rotate. But in AC motors, such as this induction motor, we don't need to change the polarity because the current itself is changing its polarity, as it is an alternating current. And that's why we use a continuous slip ring to provide the input to the rotor. Okay, now Tesla was the first manufacturer to use induction motor in their first generation cars. They don't use induction motor anymore. They use something called as internal permanent magnet synchronous reluctance motor. We are going to look into them. Okay, so let's move further ahead into the AC motors and let's look something which is similar to a BLDC motor or brushless DC motor. This is the PMSM motor or permanent magnet synchronous motor. So yeah, the construction is sort of similar to a brushless DC motor. The rotor part is it is slightly complicated, but the functioning is quite similar to a brushless DC motor. Now, the term synchronous over here, I didn't mention this earlier. Induction motors are also known as asynchronous motor. So synchronous speed is something which which I would like to highlight here. Synchronous speed is the speed of the rotating magnetic field which is generated by the stator. Okay, so induction motors The squirrel cage induction motor don't like the rotor does not rotate at the same speed as the speed of the rotating magnetic field generated by the stator, and that's why it is known as asynchronous motor as well. But when it comes to PMSM motor or permanent magnet synchronous motor, the controlling strategy is used in such a way that the speed of rotor is in sync or is in sync, like it is rotating at the same speed as the speed of rotating magnetic field of the stator. And that's why it is known as permanent magnet synchronous motor. Okay, so similar to a brushless DC motor, the magnets are mounted on the rotor while windings are provided on the stator. Now, like you can see over here, the rotor part it looks sort of complicated. There is a reason for this because the magnets are mounted at a certain angle. They have been optimized. That angle have been optimized to be mounted so that the magnetic field, the stator magnetic field, can be concentrated in such a way that this motor can provide high torque. Okay, and secondly, it has higher efficiency. It has better efficiency than BLDC motor, and simultaneously, the core losses that are being induced in motors is pretty less in PMSM motors, and the torque repel is also minimal, and that's why these are the most highly preferable motors for any electric vehicle, and many of the manufacturers are already using it. And to make this clear, this is not a solid rotor. This rotor is made of multiple iron laminate sheets. Okay, for the guys who are from mechanical or automobile background, they are just sheets of iron which are being placed together, pressed together to create one entire rotor. Okay, there are various ways of making these type of rotors. They can be either axially laminated or they can be either transversely laminated. Okay. So in axially laminated, this is a type of an axially laminated rotor, whereas in case of transversely laminated rotor, the parts would be connected from the perpendicular point of the axis. So like this is the axis, right? This is the axis of the rotor. So in transversely laminated rotor, the rotor parts would be mounted in the perpendicular direction. Okay. There are issues with transversely laminated rotors because as the rotor is the rotating part, it will have some centrifugal forces acting on it. And these centrifugal forces can pull this transversely laminated part out and the motor can get damaged and stuff. So that's why manufacturers don't prefer transversely laminated motors. Instead, they prefer axially laminated rotors. Okay. So this was permanent magnet synchronous motor. The next thing I would like to talk about is switch reluctance motor. So switch reluctance motor is sort of similar to a squirrel cage induction motor because we don't provide any electrical input to the rotor here. And also we are not using any permanent magnets over here. So the rotor is made of salient poles. So you can see over here, there are like poles on the rotor and it is made of, it is made of iron sheets. Okay, laminated iron sheets pressed together to create one entire rotor. Okay, and what is done in switch reluctant motor is that the field of stator winding, the stator windings have been they can be either switched on or they can be off. The polarities are not getting reversed. So you can see in this animation, only one pair of winding is getting switched on, and based on that, like the rotor is getting attracted towards it. Like the fundamental is similar to the induction motor, the squirrel cage induction motor, that the stator will create an it will induce an electric current in the rotor, and the rotor will have its own magnetic field, which will be attracted towards the stator winding. And that's how this switch reluctant motor also works. But the case is that here we are using a sort of we are switching the windings only on or off. The polarities are not being reversed. So we are only I suppose you understand this, right? We are only creating a single magnetic field. Okay. So the issue with switch reluctant motor is that whenever the rotor jumps from one pole to another pole, there will be a torque ripple. Okay, it will jump. It won't smoothly transition from one rotor to another. It will just directly jump from one to another. And because of which it will create a torque ripple. And that's why that's why manufacturers don't prefer switch reluctant motor, but they use something called as synchronous reluctance motor. So again, as the term comes synchronous, the rotor is going to rotate at the same speed of a rotating magnetic field. And as reluctance is here, now I would like to highlight the definition of reluctance. Because reluctance is something that in our electrical machines or electromagnetic machines, reluctance is a term like it is, to define it easily, anything that can resist magnetic field is highly reluctant. So an ion an ion can accept magnetic field easily. That means it is it has low reluctance. While air, it has high reluctance. It doesn't allow the magnetic field, like it doesn't accept the magnetic field as easily as iron can. So like iron actually helps the magnetic field to be focused, to get concentrated, while air will let the magnetic field to be spread out. Okay, so that's reluctance. And this synchronous reluctance motor uses that property of iron and air to make the rotor rotate. Okay, so as you can see over here, this is the unique looking rotor for you guys. I can assume that because you can see how complicated this rotor looks like. So these are air gaps provided in the rotor. Okay, and the rest is laminated iron sheets. Again, every rotor is going to be made of laminated iron sheets pressed together, okay, in such a way, like in every motor. And in this case, synchronous reluctance motor, there will be air gap provided in between. So what this air gap and iron sheets do is, they create a high reluctance zone and a low reluctance zone. So because of which the magnetic fields can get concentrated through the iron part, while the air will provide a high reluctance part, and this together, the difference of high reluctance and low reluctance together, they can provide, like the straight rotor can provide high torque. And the issue with one of these motors is like when you're not using permanent magnet, the motor will not act as a generator as efficiently as the proper generator. Okay, and there are so many benefits of synchronous reluctance motor that Tesla actually wanted to use it. But just because there were no permanent magnets in the rotor, they tried to change the design of this motor a little bit. What they did was added magnets into the slots, added magnets into the air gaps. So the magnets in itself can provide like better torque, plus when we don't supply any electrical input to the stator, the magnets will actually generate. Like if the vehicle is in motion, the rotor will have its momentum itself. It will be rotating as well. And because of this, the magnets would rotate. It will create a rotating magnetic field, and these rotating magnetic field will create a electrical current in the stator windings when the motor is not supplied with electrical current. Okay, so because of the magnets, now these synchronous reluctance motor can act as a generator as well, and they can provide good characteristics of regeneration. And that's what Tesla came up with. They called it the IPM. It means internal permanent magnet synchronous reluctance motor. Okay, and this motor has the benefits of both worlds. It has the benefits of a synchronous reluctance motor, that it can provide high torque, while the permanent magnets can provide better regeneration, and it can be used for regenerative braking. Okay, so these were up till now, whatever we have seen, or whatever types of motor that we talked about, all of them are radial flux motor. Okay, so basically all of them were radial flux motor because the flux that was generated, the magnetic flux that was generated by the rotor, was generated in the radial direction. Okay, so this is the axis. This is the axis of the motor. When we look at from the front, this is the axis. So the magnetic flux that was generated in this type of motor was perpendicular, in the perpendicular plane of the axis, and that's why these are known as the radial flux motor. And in radial flux motor as well, there are two different types: inner rotor motor and outer rotor motor, based on which part of the rotor, like where we are placing the rotor. Okay, if the rotor is placed within the stator windings, which is in this case the left side image, we can see that the rotor is in between and the magnets are mounted on the rotor. And this is an inner rotor motor. Basically, every manufacturer uses an inner rotor motor. Let that be electric, let that be four-wheelers, let that be your trucks, let that be your two-wheelers. There are two-wheelers that uses outer rotor motor. We will get into that. But basically, every manufacturer uses inner rotor motor because they can provide high torque. But there are times when we when we can get the advantage of outer rotor motor. So in outer rotor motor, the rotor is on the outside portion and the stator is in the between. Stator is in the center. Okay, and these type of motors are also known as hub motors. you would be aware about something called as hub motors, which are used in electric bicycles, and also Revolt RV300 uses a hub motor. So those kind of motor uses outer rotor motor, and as the rotor is on the outside, it can directly be mounted with the wheels, or the wheel rim can be designed around it, and it can directly be mounted with the wheel. But the issue with outer rotor motor is that it cannot provide high power. So like let's say the package sizing for a 1.2 kilowatt outer rotor motor would be quite big compared to the package sizing for an inner rotor motor of the same capacity, 1.2 kilowatt. But but as soon as you go above, like as soon as your power requirement and the torque requirement increases, which is definitely going to increase, let's say for 4 kilowatt, which is used in, I guess, Ola. And in that case, the construction of outer rotor motor would become complicated, and it will actually be enlarged. Okay, so you can't actually use that type of motor for any two-wheeler. So that's why then manufacturers prefer to use inner rotor motor, because the sizing and the packaging of the high capacity motors in inner rotor motor is quite minimal. It is quite small, and it can be housed anywhere in the two-wheeler. Like it can be efficiently, the space can be utilized efficiently. Okay, so that's the advantages of inner rotor motor. And these are, even in this case, even in the case of rotor as well, there are something called as surface mounted rotors and IPM rotors. IPM as in this one itself, internal permanent magnet, like the magnets are mounted internally in the grooves which are provided in the rotor. But there are also certain this rotors where the magnets are mounted on the surface of the rotor in this way. But the issue with such rotors is that, again, because of centrifugal force, as the rotor is going to rotate, because of the centrifugal force, and if the adhesion between magnet and this rotor material it reduces, there are chances this magnet can get off and fly, and it can damage the entire motor. So that's the reason why, if the rotor is on the inner side, like if you are using inner rotor motor, then the magnets will not be mounted on the surface. Manufacturers prefer to mount on the internal side. But when we are using outer rotor motor, the magnets are definitely going to be mounted on the surface of the rotor. Okay, so yeah, these were all the types of radial flux motors. Now let's talk about something unique, which is not talked about that frequently. That is axial flux motor. So in this case, the flux that is created by the stator is actually created axially or parallel to the axis. Now, as this is the axis of the motor, these are the windings. This is the stator, and you can see these are the windings. And the flux that will be generated in this type of motor would be axial. Okay, it will flow from one side to another. Okay, in this way, and that's why these are known as axial flux motor. And because of this, we can use disc-shaped stators and rotors. So this is the rotor. Magnets are mounted on the rotor surface. These are the magnets. And similarly, this is another stator. Now, as the magnetic field is going to be generated axially, it is going to spread on both sides of the stator. And we don't want one side of the magnetic field to be wasted. And that's why we can use two rotors on each side. And the benefit of this type of motor is that it can provide as much torque you want, as much torque you require, it can provide it. There is a relevance between the diameter of the rotor and the torque itself. Like if you increase the diameter of the rotor, it is definitely going to provide you higher torque. If you reduce the diameter of the rotor, this is done during the designing phase itself, it will provide low torque. Okay, so based on how much torque is required, these motors can be designed, and the packaging size is so small that the entire size, like a 300 HP motor, like this is used by Koenigsegg in their hypercar named Jumeirah, and they had renamed this type of motor into Raxial motor, RAXIAL, Raxial motor, because those type of motor, like they are claiming that their motor is using both type of magnetic flux, which is axial and radial, but they haven't, like, to keep their patent in, like to keep secrecy, because they have patented the design. They have not showcased what kind of technology they are using to create both type of magnetic flux. So that's why I would like to just mention that axial motors are already being used by Koenigsegg, and they have designed it, and their motor is just 30 centimeters in diameter, and it can provide up to 300 horsepower. So if you want to convert it into kilowatt, you can just multiply it with 0.746 and you can get the kilowatt value. So yeah, these are all the types of motor. I highly prefer axial motors because the package sizing is quite small and it can provide high torque, and high torque is highly required for our EVs. And yeah, one thing is for sure that these type of motors can be used as in-wheel motors, like in-wheel motors in the sense that the motors can directly be mounted with the wheels itself, within the wheels itself. And you guys might have seen this video of Hyundai Ioniq, I suppose. I don't remember the term, but you might have seen that how that particular vehicle has high steering angle because they were using servo motors directly mounted on the top of their wheels, and that servo motor can make the wheel to rotate at about 90 degrees. Okay, one wheel to rotate at 90 degrees. And that type of steering system had axial flux motor mounted on it. So I've actually made a video about it. So you guys, if you might have come across that video, maybe. So yeah, so these are axial flux motors. These are all the types of motors that are highly being preferred. Basically, we manufacturers like to use BLDC, PMSM, and internal permanent magnet synchronous reluctance motor. And these are something new, axial flux motor, and there is a possibility that we will see axial flux motor used in our vehicles as well. Okay, so now let's go into the side of how to select a motor or how to size a motor. So whenever we are designing any electric vehicle, we are going to start with component selection, and we are going to decide, like we would have a certain data, or we would have certain parameters already fixed that we want a particular car to, or the particular vehicle that you're designing to go up to the speed of 120 kilometer per hour. And based on that, you can actually, and to achieve that type of speed, you need to have certain power output or the torque output from the motor. And we are going to look into those calculations and how to do those calculations to get the proper sizing or the proper, or how to get the proper power output of the motor, or how to select a motor based on how much power is required to get on that speed, on those speeds. Okay, so to size any motor, we have to first look into the forces which are acting on the vehicle. Now there are three basic forces that act on the vehicle, or any vehicle. One is aerodynamic force, second is rolling resistance, and third is gradient resistance. Aerodynamic force is nothing but the force, the resisting force by the air which is acted on the vehicle when the vehicle is in motion. Then rolling resistance is the frictional force or the frictional resistance that is acting on the contact patch of the tire and the road surface. And lastly, we have the gradient resistance, which is nothing but the gravitational pull. It is the gravitational pull when the vehicle is climbing a hill, or it is being driven on a slope. Okay, so we basically consider these three forces while calculating the power requirement for any vehicle. Okay, so first and foremost, let's look into aerodynamic forces. So basically, there are two forces that act on the vehicle. One is the drag force. Two aerodynamic forces that act on the vehicle. One is drag force. Drag force is nothing but the force acting opposite to the motion of the vehicle, or the motion of any object which is surrounded by a fluid. And in our case, the fluid is air. And as our cars are submerged in air, so there will definitely be some resistance force acting on the vehicle when it is moving by the air. And that particular force is known as drag force. And then there is a lift force, which is nothing but a component, or it is a resultant force due to the drag force. It acts in the upward direction. And lift is something that we never desire, because we are not trying to design an aeroplane. We're actually trying to design a car. If you are designing an aeroplane, then yes, lift is good for you. But in case of our cars, we don't want our cars to fly, because then it's going to result into a bad accident. So we don't want our cars to fly. So we avoid lift. Instead, we try and generate downforce. Okay, downforce are good for our vehicles. Lift is not. But again, more downforce would also result into more drag. So yeah, we need to fight between that. Okay, so drag force is what you are going to consider while calculating the power requirement. So drag force is calculated with a simple formula. FD is equal to 1/2 rho V square CD into A, where FD is the drag force, rho is the density of air, V is the velocity of the vehicle in meter per second, CD is the drag coefficient, and A is the frontal area. So I would like to point this out. Density of air actually keeps changing depending on the temperature, on its temperature. So a hot air would be less dense compared to a cold air, because the molecules are going to be parted apart from each other when the air is heated up, and that's why the density of air reduces. Okay, so usually what we do is we calculate the drag force from CFD analysis of wind tunnel testing, and based on that we calculate the drag coefficient. So for calculating drag coefficient, we use the same formula. We have just shifted the terms from one side of the equal to sign to the another side. Okay, so as I mentioned, as I said, that we calculate drag force from by performing CFD analysis and wind tunnel testing. So there are pressure sensors and strain gauges mounted with the vehicle that can provide you with the values of how much force has been generated in the opposite direction because of the air, and that force can be used. That force can be used in this particular formula. That force is nothing but the drag force, and we know how to calculate the frontal area. I just posted a video yesterday about this car, Pininfarina Battista, and I did a small on paper drag force analysis on it. And I have shown how to calculate the frontal area for any car in it. So it is nothing but we just draw a simple grid, and we just do basically we should be doing the basic integration, where integration is used for finding the area under the curve, and the outer shape of any car is nothing but a curve. So yeah, that's how we find frontal area. But let's say in case of velocity is what we define. We need to define how much fast our car should go. Let's say if you're designing a Formula 1 car, then your velocity must be 300 kmph. But let's say you want to design a commuter car that can be used on weekends for traveling, then your maximum speed should be 120 kmph. So that's how you get your velocity. But yeah, convert it into meter per second, okay, not in kilometer per hour. And density, we can assume the density to be 1.225 or 1.227, but based on the climatic condition, the density also changes. So yeah, once we have all the parameters, we can calculate coefficient of drag. Now, just remember this formula, because of this formula, we can see that how power can be highly affected because of the drag force. So the power requirement, to calculate any power, just to calculate the power just to overcome drag, it is a simple formula. We just multiply velocity with the drag force, which is Fd. And if we put the formula, and we can come across that power increases in such a way with the power of 3. Like if the velocity is doubled, let's say you were driving your car at 20 kmph, and all of a sudden you have just pressed the accelerator pedal, and now your velocity of the car is 40 kmph. So technically your velocity has been doubled up. So that means you are now running at a velocity twice than the previous one. So the power required to overcome the drag force at 40 kmph would be 8 times more than the power required to overcome the drag at 20 kmph. Why 8 times more? Because your velocity is not twice, and when you find its cube, it is going to be 8 times more. So the power would increase by the power of 3. The power required would increase by the power of 3 with respect to the velocity. Okay, and that's why drag force is quite important whenever we are designing any electric vehicle, because electric vehicles are something that we have this issue of range anxiety. Okay, we care about range. How far can the car go? 300 kmph is not 300 kilometers is not enough, even though it is enough actually. But people think it is not enough. Why? Because they are worried. Like, what if the battery discharges? And the battery can be discharged because when you're driving on highway, there is going to be high amount of drag forces acting on the vehicle, and majority of the power is going to be utilized to overcome that particular drag. And that's why we need to design the outer body of the electric vehicle in such a way that not much drag force is induced on the car, and so that it becomes highly efficient. Okay, I have done a simple example using MATLAB. I took 4 cars with 4 different drag coefficient and 4 different frontal areas, and I just did how the power is going to increase with respect to the speed of the vehicle. So you can see over here, the third vehicle number 3 has most drag coefficient, coefficient of drag, and it has the highest frontal area, 2.5 meter square. Okay, so in that case, you can see vehicle 3 requires so much power to overcome drag at 120 kmph. Here. You can see over here, at 120 kmph, it requires the most drag compared to other 3 vehicles because it has higher frontal area and plus it has higher drag coefficient. So what we try to do is we keep the frontal area as minimal as possible. And basically to reduce the drag, we need to design the body in such a way that the gaps between the panels of the outer body must be seamless. So there are certain things, certain aids that can be used to reduce the drag that we are not going to look into today, because we are focusing on the electrical portion, the powertrain portion of the electric vehicles. So that's why, yeah, from this you can understand that how power increases, the requirement of power increases with the increase in the speed of the vehicle or the velocity of the vehicle. Okay, and that's why you need to design your vehicle in such a way that it has less drag inducing on it. Okay, so the next resistance that is acting on a vehicle is the rolling resistance, which is nothing but the friction between the tire tire and the road surface, where the tire is contacting the road surface. And that resistance can be calculated using the simple formula. Fr is equal to mu W cos theta. Fr is rolling resistance, mu is coefficient of friction, W is the mass of the vehicle, and cos theta is the angle of the slope or the gradient of the road surface or whatever surface the vehicle has been driven on. So this new value changes based on what kind of surface the vehicle has been driven on. So in our case, which is asphalt or let's say I don't remember the term, concrete, sorry. So in concrete and asphalt, you can see the coefficient of friction is 0.8 to 0.9. But as soon as we are driving on gravel, the coefficient of friction decreases 0.6. And if you are driving on ice, which rarely happens in India, but still, we need to consider the coefficient of friction, which is the least, and it is 0.1. And in that cases, the vehicles actually slide. The slip angle goes pretty high. There is barely any control on ice. So that's why in winter conditions in Canada and USA, people don't tend to travel on road. Okay. So yeah, we need to consider rolling resistance as well. And lastly, we have gradient resistance. Gradient is the angle of the surface on which the vehicle has been driven on. So it is nothing but the gravitational force which is pulling the vehicle down. That is the gradient resistance. And it is calculated by this simple formula again. Fg is equal to mu W sin theta. Okay, theta is the angle. Okay, in this image, it is showing alpha, but we consider theta. Okay, and mu is again the coefficient of friction, same one which we used in the rolling resistance, and W is again the mass of the vehicle, and theta is the angle of the gradient. So once we have all the three forces, the drag force, rolling resistance, and the gradient resistance, all we have to do is add all of them, and that's how we get the total tractive effort or the total force that is required to be overcome by the electric motor so that the vehicle gets into motion. Okay, or it is like the peak power that is required for the motor. And once you have the tractive effort, that all you need to do is you need to multiply tractive effort with velocity, and that's how you get the power. This will be definitely in watts. Okay, and yeah, that's how you get the value of power. That's how you get how much power is required from your motor to run on a certain speed, to make the vehicle run at a certain speed. Okay, now I would like to point this out. You don't have to consider all three resistance or all three forces at the same time. It entirely depends on what kind of vehicle you are designing. Now, let's say if you are participating in Formula Imperial or Supra or Formula Bharat, that means you are designing a race car. And that race car is going to be driven on track. So most of the time, your track surface is going to be flat. So at that time, you don't want to consider your gradient resistance and the cos theta as well. This portion is not considered when you're driving the vehicle on a flat surface. Okay. And in that case, yeah, drag force is very important because your particular race car is going to be driven at high speeds. It can be 80 kmph, it can be 120 kmph, whatever speed you are desiring for that vehicle to go. You definitely need to consider drag force in that condition. But let's say you are trying to design something called as a solar vehicle, a proper commuter vehicle. Then you need to consider all three resisting forces. But in that case also, our road doesn't have gradient in every portion of, like, there is barely any gradient on every portion of our road. Okay, whenever the vehicle is climbing a bridge, then yes, definitely the vehicle has to overcome that gradient. But majority of the times, or some portion of the times, the vehicle is going to be driven on flat surface. So in that case, drag force can be neglected because the velocity of the vehicle in city conditions, in city traffic is minimal. So if you want, you can still calculate drag force in that condition, but if you want, you can neglect it as well. Main is rolling resistance. Rolling resistance is something which is going to be acting on every condition, in every condition. Okay, so you need to consider rolling resistance in every case. So, and second thing, what I would like to highlight this is barely any manufacturer directly mounts the electric motor or the traction motor directly with the wheels. Okay, there is always a single speed reduction gearbox used. That single speed reduction gearbox actually provides a mechanical advantage, so which means it technically multiplies the torque. And because of which the amount of torque which is required on the wheel, it would be high. It definitely is going to be high. But because of this single speed reduction gearbox, you can actually size the motor to have lesser peak torque. Okay, because that torque can be multiplied by the single speed reduction gearbox. If you want, you can also use two-speed gearbox. Many sports cars, electric sports cars like Audi e-tron and Porsche Taycan, they are using two-speed reduction gearboxes. Now that in those cases, the first gear provides high torque, while the second gear provides high speed.
No, it's coming, sir.
Not audible, sir.
Not audible, sir.
Okay. So from where was I not audible? Like from what portion was I not audible?
Porsche Taycan e-tron.
Okay, yeah. So yeah, in Porsche Taycan and
Sir, again not audible.
okay, now am I audible?
Yes, sir.
Yeah. Okay. So yeah, in those cases where Porsche and Audi has used two-speed gearboxes, in that cases, the first gear provides high torque and the second gear provides high speed. But there are cases in retrofitting cases. There is a retrofitting workshop in Pune that actually retrofits your engine-powered vehicles or ICEVs into EVs. They provide conversion kits, and in that cases, they uses the stock transmission of the vehicle. Okay, the stock, like let's say for example, Swift Desire. Swift Desire has a 5-speed gearbox, and they did not take out the transmission of the Swift Desire, and instead they just directly mounted the motor with the transmission case. Okay, in that case as well, the motor functioned pretty well with all 4 gears of the vehicle. But in that case, only the first gear was not it was recommended to not use the first gear because motor initially has high torque, and the main requirement of first gear in ICEV is that it provides high torque, because the power curve of any ICEV is the torque curve is not it is not flat out. It is like sort of a gradual curve. It increases linearly and then it flattens out. But in case of motors, the torque the torque that it can provide is pretty high at first instance, at initial stage, and that it reduces with time. So this is what is highly desirable for our vehicles, and in that cases, it was recommended to not use the first gear for that retrofitted Desire. But yeah, the person had shown that the gear shifting was pretty easy. There were no torque issues, or the driver didn't even need to press the clutch while shifting the gears, because whenever you lift off the pedal, whenever you lift off your foot from the accelerator pedal, definitely the motor is not going to provide any torque to the transmission case, and in that way, the shifting can be done without pressing the clutch pedal. So yeah, you can provide multi-speed gearboxes with your electric motors for depending on how much torque is required, and you can use it to your advantage. And yeah, that's it for today's webinar. If you have any queries, you can ask me right now.
Sir, can we use CVT with motors?
Yeah, definitely. CVT has its advantages. You know it, as you have already termed it, CVT has its advantages. It can provide innumerable, like it can provide n-numberable gear reductions between a certain range. Like there is a maximum and a minimum limit, but between that range, it can provide as many gear ratios as you want.
So in case of retrofitting an automatic gearbox car, so
Yeah.
should we use also torque converters?
Actually, torque converters have been obsolete for, I don't know, for plenty of time, actually.
Sir, on the slide where we calculated the frontal area. Yeah. So you told that you are having some grid for calculating the frontal area. So, yeah, that A. If you told that you are having some grid, so can you just tell something more on how to exactly calculate A? Or some.
Sorry, your voice is not audible.
Am I audible now?
Okay. Yeah. I hope I'm audible right now.
You're
Yes.
audible.
Yes.
Sir,
Good.
actually, I was asking how to calculate the area. If you will take example of Alto or 800 or Nano, anyway.
Yeah. So yeah, that's what I was saying. I was showcasing it. So you get the picture of the frontal area of the car, and viewed from the front, click a picture.
Sorry, your voice is not audible now.
Okay. I don't want to say this, but someone might be turning off my mic by mistake. Okay. If you're doing this, please don't try not to do it. Or maybe if you're pressing the wrong key, then please don't try to press that key. Okay. Thank you. So yeah, here's the thing. You click a picture of the frontal portion, like from the front side of your vehicle, so that the front view gets on the picture. You print it out, and you at this point you can get the wheel track from the specifications provided by the manufacturer. It will be provided in the owner's manual, and from that just just measure how the distance between the front wheels in the image. Okay. With that dimension and the dimension of the wheel track provided by the manufacturer, you can get the scale of the image. Okay. Once that is done, just draw a box covering the entire frontal portion of the car and draw a grid in whatever dimension you want. If you want 1 centimeter gap between each lines, you can have 1 centimeter gap. If you want 2 centimeter gap, it is entirely on you. Okay. It is entirely your choice. Okay. And both in vertical and horizontal directions. And just see how many blocks of this grid is fully covered by the vehicle. So that.
Sir, your voice is not audible.
Okay, at what point did you lost me?
Sir, the horizontal grid.
Yeah, so once you have created the grid, you know that one block of this grid is let's say if these lines are 1 centimeter apart, then your one block grid, area of one block is 1 centimeter square. Then just calculate how many blocks are entirely covered by the car. Okay, that will give you a basic idea of how much the frontal area is. Add up all the blocks and you will get a certain centimeter square value. Convert it into multiply it with the scale and you will get your value in meter square. And if you want, you can increase the number of increase that number by a decimal point or something, because I have told you to just calculate how many blocks are entirely covered by the vehicle. If they are partially covered, and if you're neglecting it, it's all right. If they are 50% covered, then count them as 0.5. Okay, and that's how you get frontal area. This is like the basic Gola method. But the actual case which I would recommend to use is the area under the curve method, which is nothing but your integration. Okay.
Sir, sorry to interrupt. Sir,
Yeah,
but we can do it in the CATIA as well.
Yeah, you can do it in CATIA as well.
We can project it on the surface.
Exactly.
And if we will trim it out the outer area, then directly we will get the area by the major car.
Yeah. So yeah, that's not doing the hard way. That's like using your smart brains. That is the best method. I shared this because not everyone has the accessibility to use CATIA or NXCAD or Solid Edge, SolidWorks. So if you are new to this, then you can do this basic Gula method. I like to call it Gula method because I did it because it was accessible for me.
So my extended question for this is that suppose now I have a van, okay, which frontal area is exactly square, no curvature.
Yeah.
And with the some frontal area, I am having one a taxi or some area which is having a very curved frontal area.
Yeah.
Okay. So then how it will affect the curvature of the frontal area on this formula CD? Because here the shape is not defined. So any parameter is not defined by the curvature of the wave. Suppose in the picture what you are showing.
Yeah.
In the bottom here the red car.
So
okay, if I will calculate the frontal area, I will get same. But if the curvature is very smooth.
Yeah. So in that cases as well, you need to go with the same method because even though industrial experts actually uses the same method, but they mostly rely on the CFD analysis. So they might calculate the frontal area by this method by projecting the frontal view on a plane because they want to calculate the coefficient of drag. But most of it can be acquired from CFD analysis and wind tunnel testing.
Sir, could you share the PPT, sir?
Sorry?
Could you share the PPT?
Yeah, sure. I can share the presentation. I will share it with ISI India and you can get it from them. So, are there any questions?
How the wind tunnel test is to be conducted, sir?
So yeah, in wind tunnel testing, usually we prefer to do it in a scale. We prefer to test a scale model. So not everyone, like we can't use a 1:1 scale wind tunnel at every instance, right? Not everyone has the accessibility to use a gigantic wind tunnel in which an entire car can go. Although there are wind tunnels, but not everyone is easily accessible to them. So in that cases, if you have a small wind tunnel in your college or in whatever the testing facility is near you, in that cases, you need to get the dimension of the venturi or the throat part of the wind tunnel. And based on those dimensions, you can actually get the specification from the company from which you are testing it. And you need to develop a scale model of whatever vehicle you are designing. And it can be 1:2, like a half scale model or 1/4 scale model, or whatever can be easily placed inside that wind tunnel. And you need to have pressure gauge.
Sorry, your voice is not audible.
You need to have pressure gauges on the outer surface of the body. Simultaneously, like those pressure gauges will give you the value of pressure gradient across the body. And turned off. I thought my mic is turned off again. Yeah. So.
Sir, and one more thing.
Yeah.
Now, suppose we are retrofitting any car with the electric motor, then what will be preferred, to connect the motor to the gearbox or directly to connect the motor to the...
Now it entirely depends. Like if you have a powerful motor, a torquey motor, then you can just remove the entire transmission because it will save weight. And once you have reduced the weight of the vehicle, definitely the rolling resistance is going to reduce.
Hello.
Sorry?
Hello.
Yeah.
Sir, in case if the bridge is very steep, for example, sin theta equal to very, very maximum.
Okay.
At what level that motor can withstand, or is it the motor can easily drive that slope or that theta values very much higher?
Yeah. So usually in our cases, when it comes to gradient resistance or gradability, we assume 45-degree theta to be maximum. We assume like if any vehicle can be driven at a 45-degree gradient, that means that the gradability of that particular vehicle is 100%.
Okay.
So it is highly unlikely to go beyond it in any condition, like beyond it in our road conditions. The theta value is going to be somewhere around maximum 10 to 20 degrees.
Okay.
But if you are designing something like, let's say, Mercedes G-Wagon, G-Wagon has almost 100% gradability. So in that case, you have to consider the 45-degree gradient angle. But there are rock crawlers, they are not in India. These are the off-road vehicles which have been modified or customized by the owners. And they have high ground clearance, pretty enlarged wheels, and powerful engine. And those type of vehicles actually climb rocks, and like they actually climb wall of rocks. And in that case, the theta angle goes beyond 45. So
Yeah, that's my thing, because always we are considered for the race car or the flat surface.
Yes.
In case of the vehicle for all-terrain vehicle or off-road vehicle, whether we have to consider the theta value or we can omit that cos theta and sin theta.
Yeah, for road vehicles, we can omit the cos theta, sin theta, but not for for race cars. Yeah, definitely you can omit them. But for a road cars, you need to consider a certain value, because our road cars are going to climb a bridge or an overbridge or a flyover.
What is the maximum value considered in Indian scenario?
20 degrees, 15 to 20 degrees.
Okay.
Yeah. So, are there any further questions? So I'm assuming there is no question at this point, and it's all right. If you don't have any questions right now, then and if any question arises in future, then you can contact me on my links. You can contact me on my email ID or on my LinkedIn. And I have a YouTube channel as well. And the way, someone asked me about how to calculate the frontal area, I have showcased how to calculate the frontal area in my latest video. So if you want, you can check that out. And I have published 2 books, Engine in a Nutshell and Powertrain Systems in a Nutshell. And you can check them out. And simultaneously, I'm working on my 3rd book, which is Electric Vehicles in a Nutshell. And this particular webinar actually was sort of like, I just gave you a glimpse of my 3rd book, which is Electric Vehicles in a Nutshell. And it will be published soon. I'm planning to publish it in next month. So yeah, thank you for giving me your time. Thank you, ISI India.
Hello.
Thank you, Pruvang, for a session. It was a very nice session. I hope all the learners will get to know about complete motors of electric vehicles. Thanks, Pruvang, for your valuable time.
You're welcome, sir. You're welcome. Yeah. And I suppose there is a question from someone, someone has a question?
Yeah. So actually, do you have any plan to have any station on the controller or something like electronic motor?
Maybe if ISI India plans it out, then yeah, I wouldn't mind giving a session on electronic control unit, or let's say this motor control unit.
Yeah. Okay, thank you.
Many learners will plan accordingly, for the sessions.
Sure.
And it will be informed to you over the mail as well. Yeah. So Kashish will say some words about our programs as well. So Kashish, over to you.
Thank you. Hello, listeners. Thanks for attending the webinar. I hope you all like the webinar and looking the exposures to enhance your learning and skills in the same domain. Okay, you can raise your hand if you feel this webinar was helpful for you and your learning. You can raise your hand or you can comment yes or no. Okay, thanks for your response. So here I would like to introduce ISI India products, which will help you enhance your skills. So come take a look of a small video about ISI India.
Do you also want to expand your knowledge of electric vehicles and want to secure a good job in the automotive industry? Let me help you to get there with our online and offline products. ISI India has been offering specific domain courses as per the industry demands with perks like pay after placement, no cost EMI, placement assurance, global wide certification by Automotive Skill Development Council ASDC and National Skill Development Corporation NSDC Government of India. We have a range of courses in electric vehicle, computer-aided design and engineering, including postgraduate certification and executive PG program in EV, professional master certification program, specialization programs, fundamental programs, and internship in EV, CAD and CAE. Our postgraduate certification program in EV is specially designed for the students with 120 plus online learning hours, 100 plus hours of industrial projects and internship.
Ma'am, voice is not audible.
Audio seems to be off.
Hello engineers, do you also want to expand your knowledge of electric vehicles and want to secure a good job in the automotive industry? Skill themselves or looking for a career change in the EV industry with 120 plus online learning hours, 20 plus hours of industrial projects. It is a 9-month assured placement course with globally valid certification from NSDC and ASDC Government of India. Our professional master certification program in EV, CAD and CE is specially designed for the undergraduate students to pave their career path by providing industry relevant skills with 100 plus online learning hours, 5 plus hours of industrial projects. It is a 6-month placement assistance course with globally valid certification.
Madam, please share feedback from me.
Projects. It is along with the courses for skilling, reskilling and upskilling at engineering institutes across India. We are setting up a state-of-art facility center of excellence for e-mobility research and skill-based education, which is equipped with research and project-based learning-oriented experimental setups. This center of excellence is not only limited to educate the students, but also it will be utilized for research, innovation and product design and development. It is a combination of 6 labs including EV powertrain training and research lab, battery BMS training and research lab, EV charging and battery swapping lab, software modeling and simulation lab, innovation lab and renewable energy lab. Each lab is consist of number of customized workbenches and machineries. Few of them includes EV drivetrain experimental setup and motor testing workbench, hybrid drivetrain experimental setup with data logger, EV machine cutout section workbench, 2-wheeler, 3-wheeler, 4-wheeler training workbench, battery load capacity testing, battery BMS with CAN protocol workbench, V2G setup, on or off grid work charging station, battery swapping, autonomous vehicle training workbench, solar power generator and software solutions and many more. No matter from which branch you study, we commit to skill and assure you a success in your career. We have spread the joy on thousands of faces, becoming their partner along with the journey towards success. Join us and take advantage to unlock endless career opportunities.
Okay, thanks everyone for watching this video. Hope you guys have understood the products of our company. So any of you wants to enroll in the courses or interested in the course, kindly send us the inquiry through a QR code displayed on your screen. Thank you.
Madam,
Please
kindly
share your feedback.
from me, madam.
So learners, like if you are interested in joining our program, so you can scan our QR code. This QR code is only for the courses. Okay. So we are having like pay after placement program as well. Okay, for the working professional and for the students as well. Okay. So if you're willing to join our courses, so you can scan our QR code. Feedback form link is shared in the chat box. You can also give the feedback regarding the webinar as well. Okay. And if you want to join our courses, so you can scan our QR code. Okay. Our counselor will connect with you like within 24 hours. Then it's like if you are like done with all the, like we have done with the session, okay? So you can leave now. Like if you are interested in joining our programs as well, so you can scan our QR code. We were done with the session. Okay? You can leave for the day. And the certificate link will be shared over the mail after 7 p.m. today. Okay, you can download your certificate for the webinar. For the courses, you can scan our QR code. Thank you, learners, for joining our webinar. Okay, for the upcoming webinar, the details will be shared once again right over the mail.
Hello.
Yes, please. Yes, please ask.
Sir, like how do a student become a member of ISIE?
Okay. For that, you have to enroll with our membership program. Okay.
Okay.
Yeah. So you can share the query at our website. Like you want to join our membership. Okay. So our counselor will connect with you for the details. And can you please confirm your name so that I will inform Danish, right?
Yeah. Sure.
Okay. So Danish, by tomorrow our team will connect with you for that. Okay. Or else you can leave the query. Okay.
Okay, sure. Thank you.
Thank you, learners, for the webinar. Like you have joined the webinar and you got to know about a lot more about the motors. Okay. For the upcoming webinar, the link will be shared amongst you guys. Okay. Within 24 to 40 hours. Okay. Have a great day, guys. Bye-bye.